Here we are back at this same slide where we ended last time, comparing the SN1 and SN2 mechanisms. These are the two primary pathways by which substitution reactions occur. And which one of these mechanisms is at work greatly affects how fast the reaction proceeds, and in some cases can affect the products that you get from the substitution reactions. And we'll talk about a little of that later on. I want to show you here some animations that compare these two pathways kind of in motion here. This is a molecule of what might be a tertiary butyl chloride or bromide molecule. I think they let bromine be represented by the color red here. And so this shows the substrate, and I'm going to animate this, and it's going to show the carbocation forming here. And this kind of goes forward, and now it's going to back up and do it again. But in the forward direction, you can see that red atom is being removed, and notice that as that happens, this carbocation changes its geometry a little bit. That is a real effect. It goes from having that tetrahedral shape to having a trigonal planar shape where all of the carbons are in the same plane. So if I move this around, you can kind of tell that everything is coplanar once that red atom is gone. And so for tertiary and most secondary alkyl halides, this is the first thing that happens when they undergo substitution. You create a carbon making only 3 bonds, which is why it would have that positive charge. I'm going to contrast that with a little movie here, an animation for SN2. So with SN2, we tend to see that with primary alkyl halides or a methyl halide, and that's what we have here, a methyl bromide perhaps. And this incoming nucleophile, this green atom, is going to do a substitution, but as I play this animation, notice that we don't have a point where a carbocation forms. And this is going back and forth as well. I guess it is a reversible process after all. The key is that that carbon never develops a full positive charge because it never exists with only 3 bonds to it. And so we've got bond breaking happening and bond making, and that's kind of the essence of SN2 and how it's distinguished from SN1. We assume that this is the kind of mechanism that's going to occur in cases where we wouldn't expect the carbocation to be particularly stable, and that's going to be certainly the case if we're dealing with something like a methyl bromide. And so on this slide, that's what's being shown on that bottom picture there, is the incoming nucleophile coming in at the same time that the leaving atom is leaving. So we say the SN2 is a concerted mechanism in that regard. And again, we assume that SN2 is going to be the preferred method of reaction when you have either a methyl group or any primary alkyl halide, so that they are not forced to make what would be a very unstable carbocation. This next slide also indicates why SN2 is favored for methyl and primary alkyl halides, and why, just as importantly, we don't see tertiary alkyl halides engaging in SN1 reactions. At least the rate is not very fast. So this is again the transition state of SN2, and we're comparing a methyl bromide with a hydroxide as the incoming group versus a tertiary butyl bromide. And the point of this picture on the right is that the OH group really doesn't fit. The 3 methyl groups here are rather bulky, and so their size prevents the hydroxide from being able to create a bond to that carbon right in the middle. So just as we assume that things like methyl groups don't make carbocations, and so they avoid SN1, it's also true, on the other hand, that things that go by SN1 that can make stable carbocations, they are discouraged from undergoing the SN2 mechanism because of the bulkiness, the steric effects, as it's called, of having this tertiary environment around that carbon.